Now that we know the results from convex analysis, we can now define and prove this celebrated result of single object allocation called the Myerson's lemma. So for that, we are going to define something called monotonicity of an allocation rule. So we are going to say an allocation rule to be non-decreasing if the following thing happens: if for every agent I and for every t minus I, so the type profile of the other agents, we have the following condition satisfied, that whenever ti is strictly greater than si, the corresponding allocation is going to be non-decreasing. So it is saying that if an agent had a type of si, and if it increases its type to be to ti, if the probability with which it was getting that object, that probability can just weakly increase. So that is the meaning of a non-decreasing allocation rule. So all the allocation rule that satisfies this property is called a non-decreasing or monotone allocation rule. So now let us come to the result by Myerson, which actually gives a characterization of all the dominant strategy incentive compatible mechanisms in the context of allocating one single indivisible object. So let us assume that the type set of all the agents are between 0 and bi. So it's an interval between 0 and bi. Bi can differ, but everyone's lowest value for that object is 0. And the valuations are in the product form. This means that if you have a probability of allocation as pi and your value, the value for that object is ti, then your expected valuations or the valuation for your object under that rule is nothing but pi times ti. The allocation rule f, which is mapping this type profile into an allocation, which is a randomized allocation, and a payment rule which has this components p1 to pn for each of these agents, is going to be DSIC if and only if two conditions hold. And what are those conditions? The first condition is f is non-decreasing, the property that we have already defined in the beginning, that if your valuation increases, then your probability of getting that object weakly increases. And the second property is that the payments are going to be given by a very specific integral formula. Let us read it one by one. So the first part, you can denote that. So this is the payment for agent I when the type profile is ti minus I. And it has one component which is a constant component from the view of player I. It may depend on t minus I, but because in this context from the view of player I, the types of the other agents is held fixed, so it is like a constant for that player. So we will typically refer to this component as a constant component of the payment function. So the second part is its value, so something like ti times the probability with which it gets this. So this is something that in the product form, this is the value of that agent for this object. But then there is this negative integral form, which is integrating between 0 and ti, the integral, the probability of allocation of that agent. So we will see what are the implications of this integral formula when we discuss examples and we prove this result. But at this point, it is just this integral formula. So the first remark that we are going to make is that this is a little different. So we have seen the characterization of truthful mechanisms even for Roberts' theorem, for the affine maximizer results by Roberts, but that gives a very specific functional form, while Myerson's result is giving a more implicit property. It is saying that if a mechanism is truthful, then some monotonicity condition should hold. So something like it is if it has a very specific property here, then it should continue to hold that property in some other place, and so on. So let us now start proving this result. First, we'll prove the forward direction. That is, we are given that this mechanism f comma p is DSIC, then we'll have to show that these two properties should hold. So how should we go about proving it? So first we write down the utility of agent I. So utility when its type is ti and the type of the other players is t minus I. We know that that is going to be ti fi ti t minus I. So this is the valuation that this agent gets minus the payment that it is making under that type profile. And when you have a different type for that the same agent, this should change accordingly. Now, since this f comma p is DSIC, will have certain property satisfied. It is going to be at least, so we can write this utility, which is nothing but this one. When this agent is misreporting its type to SI, this inequality should get satisfied. Now, we can actually add and subtract one quantity, which is this SI, FI, SI, T minus I. So this we will add as well as subtract, and we rearrange these terms in a certain way such that we have one quantity which is here, the other quantity is FI, SI, T minus I multiplied with Ti minus Si. So you can see that this terms will actually cancel out this and this. But we want to write it in this specific form, because now we know that if we collect together these two terms, this is nothing but the utility of the same agent when its true type is SI. So this is what we have defined earlier. So this is from the second equation here. And the second term is just going to be the difference between these two types, Ti minus Si, multiplied by the Fi of Si T minus I. Now, if we go back what we have defined in the context of convex functions and subgradients, we can actually define this GTI function to be the utility function. So everywhere, just ignore the T minus I. T minus I is appearing everywhere. It is like the other agents types, which is held fixed. So we look at the utility of Ti T minus I, utility of player I when its type is Ti, and define that as the as that function GTI. And phi Ti, we are using the same notation because we want to show that this G function will be a convex function, and phi will be nothing but a subgradient of so f of Ti is nothing but this the allocation, the probability of getting that object for player I. Now this using this substitution, we can write this equation 1 exactly in the same way as we have wanted for the subgradient equation. So this is nothing but the subgradient equation. So all that we are left with is to show that this function g is a convex function. If we can show that, then we know that this phi function is nothing but a subgradient function. Alright, so we will make this conclusion after we have proved that g is a convex function. Rest of the things are falling in place. So let us now try to see why g is convex. Okay, so to do that, let's do the following thing. Let us pick two arbitrary points xi and zi in the type set of player I, and define a convex combination of that and denote that with yi. So we have a convex combination of these 2 points xi and zi, and that is defined as yi. Now what we know from DSIC, because we got this inequality of 1, so the this first equation and its reduced form when we are substituting using g and phi, this is coming as a consequence of the DSIC. We have just rearranged the expression, the condition for DSIC. So therefore we can just write that if this agent's true type was xi, and if it was misreporting to yi, then we can use this inequality to show that this is DSIC. So that is for between xi and yi, and when its true type is zi and it is misreporting to yi, you can write a very similar expression. So now what we are going to do is we are going to multiply this first inequality with lambda and the second inequality with 1 minus lambda, and then add them together. This does not change the inequality, the direction of the inequality, because both lambda and 1 minus lambda are non-negative quantities. So on the left hand side we have this quantity, and on the right hand side we have g of yi, which is nothing but this lambda of xi plus 1 minus lambda of zi. That's the expansion of yi. And the rest of the part, the rest of this right hand side of this inequality happens to be phi of yi times this quantity. Now we know that y is nothing but this quantity itself, so this part will be equal to 0. So all that we are left with, so this disappears, and what we are left with is this. So this shows, this is exactly the condition for convexity, and since we have picked arbitrary xi and zi and their arbitrary convex combination, we can say that g is convex. So we have actually proved that this function is convex. So what was g? G was nothing but the utility function. This is something that we have noticed in the very first example of the second prize auction, that the utility was convex, and its derivative or subgradient in this case happened to be the allocation function. And that is not just a coincidence. This can be seen for any kind of mechanism, any kind of truthful mechanism which allocates one single indivisible object. Okay, so so now we are going to use the fact that whatever we know as the properties of this convex function and its subgradient, we can apply lemma 3. Lemma 3 said that when you have a subgradient of a convex function, then that subgradient is going to be non-decreasing. So therefore what we have is this function fi tit minus I is non-decreasing in ti, and that is what we wanted to prove. This is the part 1 of our Myerson's result. And this lemma 4 gave some integral formula, and that integral formula is this, and we are going to use that to find the payment expression. So what can we do? We can just replace this quantities with their exact values, the actual values. So we have this utility of 0, t minus I, and this fi. So the subgradient is the allocation of allocation function under this of agent I. And then we expand it out further, because this utility is nothing but their expected valuation, expected value for that object, and minus the payment that has been made. And now we have, because this is 0, this part only remains to be minus of pi 0, because only the payment part shows up. The first part, because ti is actually equal to 0, that part disappears. So that is just this. And for the last part we have the same expression as before. Now you just rearrange and you get the payment formula that we have that we wanted to prove. So this proves the first part, the forward direction, that whenever we have a DSIC mechanism, that should satisfy these two properties. Now we'll have to show the reverse direction, that if that satisfies this monotonicity property and this payment formula, then it must be DSIC. And this proof is very easy to follow, and I like this proof because it is entirely by pictures. So what is given in this case? We are given that this function is non-decreasing, and we have that payment formula. Now let us look at the payment formula, and we know exactly what it is. And for simplicity of exposition, let's assume that pi 0 is exactly equal to 0. All that will change is the origin point here will change if we use a non-zero constant value for pi 0 comma t minus I, but that does not matter. So let us assume this. So then we don't have, so this term becomes equal to 0. All that we have is ti multiplied by the probability of allocation for that agent and this integral formula. And what we also know that this fi function is non-decreasing. So let us look at this fi function. So let us look at the function fi tit minus I, and on the x-axis we are plotting ti. So this function is non-decreasing, looks something like this. Now when the agent is not misreporting its type, so it is reporting its true type. So let's say ti is its true type, if it reports that, then what is the payment that it is making? So the first term of this payment formula is Ti times Fti, so which is nothing but the area under this this entire rectangle here, and then you are subtracting out the part which is the integral formula, the integral from 0 to Ti of that allocation. So we are actually integrating out this green part from it. So therefore the payment is nothing but this yellow section here, because we have this rectangle. Subtracting out this area under this curve is essentially the yellow one. But we also know that the utility is nothing but the utility is Ti Fi Ti T minus I minus this payment Pi of Ti T minus I. And if you do that, what you get is this part will actually cancel out, and you'll be left with this part. So this green part is nothing but the utility here for this player when it is reporting its type truthfully. Now let us look at two situations where in one case the agent is overstating its type, and the second case where it is understating it. So if it is overstating, so Si, so what changes is its payment, right? So it changes its allocation and its payment. Of course, now the mechanism will imagine as if this is the total allocation, and therefore what will change here is this term. So because payment can only be computed based on what is reported, so both this Ti and Ti here, they will be replaced by Si now. So this first term will be nothing but this larger rectangle here now, right? And the second part will again go from 0 to Si, so which means this will be this area under this curve, this entire area under this curve, and the payment will be nothing but this part here, right? So this is the payment that it is making. But now if you are looking at the actual utility, so the actual utility for this player will have this Ti in it. The only thing that changed is this Si, because player I has misreported Si, so its own type does not change, so this part will not change, so it will still have this Ti multiplied by this Fi, which will be having this large value here. So the actual valuation of this agent will have this value, and now it is making the payment of this amount. So notice that this will go all the way up to here, because the for the payment part it has no way to estimate what its true type is, so it will just calculate everything by replacing Ti with Si, and that will give it a payment of this part, right? So you can see that its valuation was this much, and it is subtracting out this larger quantity. So compared to the earlier one, it is having this part, of course, but it is also getting this negative part. So eventually this area under this curve minus the area that we have shown here, this is going to be its utility. So clearly that will be worse than this one, because now you have this area under this curve, this area here, but you are subtracting out some part. Fair enough. So that is one the part where it is misreporting its type to be higher than its true type. Let us look at the condition where it is misreporting to something which is smaller. So as before, you are going to have this the mechanism will calculate its payments as this part only, and whatever your actual utility, what it is again going to be replaced only in the allocation part, not on this Ti part, because that is the Ti that you already have. So this Ti times this part, so this is going to be the new allocation here. So this smaller rectangle is going to be the valuation part for this agent, minus the payment that it is making. So this part is going out, so it is only getting this remaining portion, so a kind of a the top part of this area under this curve, it has been chopped off. The rest of the thing it is getting at as its utility, but that is certainly smaller than the original one, this area here, because you are actually losing this part. So this also shows that if you are misreporting your type to be something smaller, then that is also going to be not beneficial for you. So we could show in using this case, this payment formula, and the fact that this is monotone, that it is essentially truthful. It is dominant strategy incentive compatible. One can show this even more formally, but the proof by pictures is much more intuitive, and perhaps will stay longer in your mind. So one corollary that we can make is that an allocation rule in single object allocation setting is implementable in dominant strategies if it is non-decreasing. So we already know what kind of payment formula we have. All that we need is to ensure that the allocation rule is monotone, and that's it. So with that, we can ensure that that allocation rule is dominant strategy implementable.